Lubricating rolling bearings is one maintenance task that deserves our attention. For those involved with reliability, asset longevity, and energy conservation, getting this job done right means everything. Still, lubrication of rolling element bearings remains a misunderstood and abused task. Can it be true that 40% of all bearings never live to their engineered life cycle, and bad lubrication practices are the leading cause of this infant mortality? This is Alan Rienstra with SDT. SDT provides ultrasound solutions that give our customers a greater understanding about the health of their factory. We help them predict failures, control energy costs, and improve product quality while contributing to the overall uptime of their assets. Friction is all around us. Without it, we'd find it very difficult to run, walk, or even stand on our own 2 feet. We need friction to drive our cars and fly our airplanes, and we need friction for our motors to drive pumps. But when it comes to our plant, machinery friction is both friend and foe. If part of your job is greasing plant machinery, then you know well the battle against frictional forces that threaten the useful life of rolling element bearings, and you definitely want to avoid these 3 common lubrication mistakes. Mistake number 1. Scheduling lubrication tasks on a calendar basis instead of a conditional basis. Greasing a bearing once per week or once a month may seem like a sensible thing to do. After all, performing scheduled maintenance at regular periods is an age-old concept ingrained early on. Even OEMs still advise best practices based on time intervals to ensure maximum asset lifespan. Are they right? Or does their advice steer us in the wrong direction? Bearings need grease for one reason only, to reduce friction. As long as the lubricant is performing that service well, there should be no need to change it or add more. Yet we frequently do, with potentially catastrophic results. Relubricating a bearing just because your calendar told you time's up is the first mistake you must avoid. Don't let your calendar overrule common sense. Instead, monitor, measure, and trend friction levels and predict precisely the right time to grease. The second mistake is adding the wrong amount of grease. Sometimes we add too much, other times not enough. Both are wrong. Too much grease builds pressure, pushing the rolling elements through the fluid film and against the outer race. The bearing has to work much harder to push the rolling elements through a mud bog of grease. Imagine for a second you're running along a beach, ankle deep in water. Your legs effortlessly drive your feet with each step, while a small amount of water splashes coolly around your ankles. You feel as though you could run forever and never get tired. Now imagine running knee-deep or even waist-deep in water. Your legs tire quickly. The water surrounds you and makes movement feel awkward and unnatural. You might grunt, you might groan and strain until, after a few seconds, you give up from exhaustion. A bearing drowning in grease will run hot. Excessive heat breaks down the grease. The whole system is an inefficient waste of energy. How do we avoid this mistake and stop at just the right amount of grease? By monitoring the bearing's friction level with ultrasound as new grease is being applied. As new grease flows into the bearing cavity, a measurable change in ultrasound levels is measured, heard, and recorded with an SDT LubeTech kit. As the decibel level approaches normal baselines and stabilizes, you know only the needed amount of grease has been added. Like any job, there's a right way and a wrong way to do things. Simply listening to a bearing with an ultrasound device that gives no quantitative feedback is a recipe for disaster. The audible feedback is too subjective to draw any comparative conclusions. No 2 people hear the same, and there's no way to remember what the bearing sounded like a month ago. So what's mistake number 3? Sacrificing quality for price. Always use an ultrasound instrument that provides a digital decibel measurement. Do not rely on stethoscopes, screwdrivers, and listen-only ultrasound instruments. Better still, use a device that provides multiple condition indicators. max and peak RMS decibel measurements indicate alarm levels and greasing intervals, while ultrasonic crest factor provides insight about the bearing condition in relation to its lubricant. Crest factor helps us differentiate between bearings that need grease and bearings that need to be replaced. Bearings reside in noisy places. Deafening, really. So many sources of noise coming from all directions. Humans are simply incapable of filtering the sound of a grease-starved bearing from other sounds. Even if we could, how would we measure the results? How can we compare what we hear today against what was heard a month ago? The days of listening to a bearing with a stethoscope, screwdriver, or broomstick are over. There's just too much at stake to rely on antiquated methods. But noisy environments are where high-quality ultrasound instruments thrive. These are the challenging situations they were built for. Take, for example, the SDT-270. It hears above the noise of the factory floor and concentrates on a narrow band of ultrasonic frequencies. Friction and bearing defects first reveal themselves in this frequency range. The SDT-270 accurately filters, measures, stores trends, and alarms the earliest signs of lubrication and bearing failures, making it the ideal tool to predict greasing requirements. It does so by providing 4 relevant data sets we call condition indicators. Condition indicators characterize the health and performance of a machine and provide more insight as to what has changed. The first condition indicator is overall RMS, reported in decibels per microvolt. Overall RMS is an averaged calculation of negative and positive values collected over a specified sample time. That sample time is defined by you, the ultrasound inspector. The SDT-270 reports the RMS by buffering 256,000 samples per second. This condition indicator characterizes the energy inherent in the ultrasound signal. RMS incorporates both friction and impulsive ultrasound over the sample time. It's a stable and repeatable value, making it an ideal value to trend and alarm to. The next condition indicator is max RMS. We also calculate that in decibels per microvolt. The SDT-270 actually calculates RMS 2 ways. The first I just described. It's an overall value for a specific time frame sampled at 250,000 samples per second. The second we call a sub-RMS. The sub-RMS consolidates the RMS into blocks of data 250 milliseconds long. So an RMS collected over 1 second would contain 4 sub-RMS blocks. The loudest block reported represents the max RMS. The max RMS is used to compare against the RMS to determine if the signal is stable. The next condition indicator we call the peak value. It's the maximum instantaneous value recorded during the measurement cycle. Since the SDT-270 takes 250,000 samples per second, the peak condition indicator is extremely sensitive to any abrupt variation. This makes it really useful for detecting impacts produced by early stages of bearing failure. For example, let us say that an alarm was triggered when the RMS value exceeded 8 decibels per microvolt over its baseline. If lubricating that bearing returns its RMS condition indicator to baseline, but the peak value remains elevated, this is an indication that the alarm was triggered by more than just lubrication issues. The bearing is entering early failure stages. The fourth condition indicator is crest factor. Crest factor is simply calculated by the SDT-270 as a linear ratio of the peak value to the RMS value. The beauty of the crest factor is how it reacts to unstable bearing signals. This makes it useful for estimating the failure severity of bearings and gears. When ultrasound inspectors put all 4 condition indicators to work, they have the power to predict lubrication requirements based on condition instead of time. RMS tells us when to grease, and more importantly, when to stop greasing. Max RMS and peak give an indication that an increased RMS value may be more than just friction at play. Crest factor helps track the evolution of failure from first to final stage. SDT's condition indicators present a fuller picture of bearing condition and take ultrasonic decibel metering to a new level. For those who want analysis beyond static condition indicators, SDT offers dynamic data analysis. Static condition indicators are useful for trending and alarming, but dynamic data analysis goes deeper and provides a visual representation of the ultrasound signal. Ultrasound data presents well in the time domain. Visually, it helps explain changes in static condition indicators. To demonstrate, let's take a look at two identical bearings. One of the bearings is correctly lubricated and the other is under-lubricated. We captured dynamic signals 20 seconds in length for each bearing. The first thing we need to do is scale the y-axis of each time graph identically so we can compare them side by side meaningfully. Let's look more closely at the correctly lubricated bearing first. The static RMS condition indicator is 51.2 decibels per microvolt, and the max RMS is similar at 51.7. A peak ultrasonic value of 67 is notable, but not alarming, and the crest factor is 6.17. Now compare this to the companion under-lubricated bearing. Overall RMS of 57.8 and max RMS of 58.7 is about 6 decibels higher than the correctly lubricated bearing. The friction level is 2 times higher in the under-lubricated bearing. The peak level is 12 dB higher, which is 4 times higher than 67. What happened when, using our lubrication procedure, we attempted to restore the under-lubricated bearing to optimal conditions? Since bearing 2 data suggests that it was in need of lubrication, our lube tech did just that. The result is visually obvious. The grease first reached the rolling elements at the 6 to 7 second mark. By the 10-second mark, the bearing was noticeably quieter, and the sharp peaks from bearing impulses are now considerably smaller in amplitude. Let's take a look at creating an ultrasound greasing program. Success is dependent on organization and commitment. Without these two structural elements, your ultrasound lubrication program will find difficulty getting traction. However, with well-organized execution, the program will be on a solid footing from the outset. Getting the commitment from all levels comes much easier when a program can demonstrate structure and cohesion. Results will prove the program faster, which will trigger easier access to funding to grow and sustain the program. There's only one clear way to create organization around a project, and that's to define goals. So start by asking, why are we starting an ultrasound lubrication program? And what rewards do we expect to reap? There is no one easy answer to that question, and probably several that make sense. Saving money is an obvious benefit that gets the attention of management, but it's not specific enough. How will an ultrasound lubrication program save your company money? By reducing grease consumption, by raising awareness of the right types of grease to use, by making more effective use of LubeTech's time, by extending bearing life, by decreasing energy consumption from overgreased motors, by contributing to a mentality of best practices that positively infect other aspects of your business. SDT has published its recommended best practice for lubricating bearings on an ultrasound condition basis. Every plant is different, but there's basic similarities that make a general procedure for ultrasonic lubrication relevant. This general procedure is meant as a guideline to be used to build out a more specific procedure for you. This may be an exercise best undertaken with the guidance of your ultrasound implementation consultant. At the end of this presentation, you can request your own copy of SDT's ultrasound lubrication procedure. How often should machines be greased? Well, there's no easy one-answer-fits-all to this question. Presuming that full faith in ultrasound condition-based relubrication is engaged, we can approach the answer with this simple logic. Why do bearings need grease? To reduce the frictional forces between the surface of the bearing's rolling elements. Okay, so when does new grease need to be added to a bearing? When the bearing's frictional forces increase beyond a set quantifiable level. What is a reliable and easy-to-use technology that determines changes in frictional forces? Ultrasound. Back to the original question then. How often should machines be greased? The answer must be when your ultrasound technology reports an increase that's 8 to 10 decibels louder than your established baseline. Knowing that 6 decibels over baseline represents a 2 times increase in frictional levels, 8 to 10 decibels RMS is logarithmically and logically an intelligent point to create a relubrication interval alarm. This sample trend graph shows a bearing's degradation over a 12-month period. The baseline ranged between 29 and 32 decibels for the better part of 10 months. Around May 2012, the bearing breached the 40 decibel mark for the first time. That represents an 8 to 10 decibel increase over baseline. This should have triggered an alarm for intervention. Lubrication of the bearing at this point to return it to baseline may prevent a further breach above 50 decibels and the next stage of bearing failure. Avoid these 3 common mistakes. Grease on a conditional basis rather than a time basis. Add the right amount of grease without over-lubricating. And use a digital decibel metering ultrasound detector instead of a listen-only tool. Now, you're well on your way to establishing a world-class condition-based lubrication program. Next step?